Nuclear power. Comprising nearly 20% of all power generated in the United States, this atomic energy is a vital component in our national energy diet. Nuclear powers our homes, our businesses, and our schools. For all the good that nuclear power does, none of it would be possible without the chain reaction. First proposed by Leo Szilard in 1933, the nuclear chain reaction was developed into the first man-made nuclear reactor in 1942 by Enrico Fermi. The chain reaction would go on to be used in the development of the atomic bomb, as well as the cornerstone of modern nuclear power. But what is a nuclear chain reaction, and how does it make power? The nuclear chain reaction begins with the humble uranium atom. As the heaviest of all the natural elements, uranium is also less stable than many of its lighter counterparts. This instability is even higher in a particular variant, or isotope, of uranium called uranium-235, or U-235 for short. While also naturally occurring, U-235 makes up less than 1% of all natural uranium, so it's a bit hard to come by. In order for the uranium to be used as fuel, it must be purified through a process called enrichment, so that its proportion of U-235 is increased from about less than 1% to roughly 5% of the total mass. This is relatively easy in comparison to the enrichment of weapons-grade uranium, which requires that the uranium be over 90% U-235. Once the enrichment process is complete, the nuclear fuel, now fitted into rods, can be inserted into a reactor core. It is here that the chain reaction can begin. A single neutron collides with a U-235 nucleus, forming an unstable U-236 nucleus for a brief moment before splitting into 2 daughter nuclei and 3 new neutrons, releasing some energy in the process. The 3 new neutrons produced in this reaction are available to collide with other U-235 nuclei and can therefore sustain a chain reaction. At this stage, the reactor is described as critical. The energy released is primarily what we call kinetic energy, or the energy of motion. As more reactions occur, more motion takes place, and this kinetic energy increases. The nuclei in the reactions vibrate when struck, producing heat. If controlled, the heat can be used to make steam, and that steam powers machinery that drives an electrical generator. Now you have power. But how do you control a chain reaction, and what happens if you don't? The ideal amount of neutrons lies somewhere in a Goldilocks zone. If too many neutrons are generated, too many U-235 atoms will be split, and the chain reaction will quickly exceed safe energy thresholds, potentially leading to an accident. However, if too few of these neutrons are generated, the plant won't output enough power, and the chain reaction may stop completely. To ensure that a steady but manageable amount of chain reactions occur, nuclear engineers utilize control rods within the reactors. These control rods are made of materials that readily absorb neutrons without reacting. When control rods are inserted into the reactor core, they capture excess neutrons, slowing the chain reaction. Through these control rods, as well as many other safety measures taken at all levels, the chain reaction can be harnessed to produce clean power for millions.